both model a times b to the x power to a e to the kx power. Okay, let's read this question in here. This problem in here first. Okay, ready? Candy, go ahead, please.
Which one? 31?
This one in 31 and 32 with the situation. Go ahead.
So everything.
Yes,
Okay.
two more.
For the following exercises, use this scenario. A tumor is injected with 0.5 grams of iodine, 125, which has a decay rate of 1.15 per day. To the nearest day, how long will it take for half of the iodine 125 to decay? And then 32, I can't see that. Write an exponential model representing the amount of iodine 125 remaining in the tumor after T days. Then use the formula to find the amount of iodine 125 that will remain in the tumor after 60 days. Round to the nearest tenth of a gram.
Thank you. All right, so let's see this one first. First of all, it already says that this one has, is it an exponential growth or an exponential decay equation for such? Madeline? Decay, right? So thank you for that one. So we can typically write that in this form. Y is equal to P 1 minus R to the T power, right? Because it's a decay equation. That's why it's minus, right? So with that being said, we can write it in this form. Y is equal to, do we have our P for such? What's the initial value of the iodine 125? What's the initial value of the iodine 125? 0.5 grams, right? So half a gram was injected, right? Iodine 125. So this is what? 1 minus R. What is R in there? What is the decay rate per day? 1.15%. Round it off to, well, you divide it by 100%, right? To convert it to decimal. So your R is what? 0.0115. We did, right? Because it's 1.15% per day decay rate. It's 0.0115, right? It's 1.15% divided by 100, right? Raised to what power? Are we good, guys, with what we did so far? Okay, so again, we convert it into our decay rate equation. And with that, we can write this one now as such. Let me go ahead and get some more fancy. So this one can now be rewritten as such. Y is equal to 0.5. What's 1 minus 0.0115, guys, on your calculators? Let's see. 1 minus 0.0115 on your calculator. What did you get, Logan?
0.9885.
Thank you, right? 0.9885 raised to the T power. Good? Right. So, let us now convert this form. What is this form? A times B to the X power, right? Now, how do you convert it into this form AE to the KX power, right? Because in that, we can get its half-life already, okay? So let's read this one in here. Step number 1. Thomas, go ahead.
Rewrite y equal to a times b of x as y equals a times e to the power of 1 times b to the power of x.
Thank you, right? So with that, we can write this one now as follows for step number 1. Y is equal to what? A, which is this, right? 0.5, right? E, ln, right? What's our B? 0.9885 raised to power T, right? So that's our step number 1. We write this A times B to the X power as what? A times E to the ln B power T. Let's read step number 2, all right? Aiden, go ahead, please.
By how y equals a to the
Thank you, right? So that means by power rule, this t can just be what? In front of that ln, right? So with that, we can write this one now as follows. Y is equal to what? 0.5 e, what's our t? Let's put it in there. Times what? ln 0.9885. Okay. Good, guys? Well, by commutative property, for multiplication, these two can just be, flipped, right? So this one, you can write this one as follows. 0.5 e to the ln 0.9885 times t. So we just flip these two, right? By commutative property for multiplication, right? We say 2 times 3 is just equal to 3 times 2. Okay. Right. Well, after that, what do we do then? Well, this is your A. This is your entire B. That is your x power or t power, right? Now, let's read step number 3. All right, Emma, go ahead, please.
This implies that k equals ln times b.
Yeah. So k is just equal to ln, okay, of, right? ln of 0.9885. Right? So that means your k in here is just basically ln of the b, which is 0.9885. Have a good, guys? Okay. Questions, guys, with what you did? Well, so what is our 31? Let's write our half-life now, right? Kylie, it says in here, can you read once again the 31?
To the nearest day, how long will it take for the half-life of the iodine 125 to decay?
Thank you, right? So how do we get that one in here, right? So let's read this one in here on how to get that half-life. Okay, so let's see it in here. What's the question again? How long will it take for half of that to decay? All right, let's see that one in here. So once again, we already have this equation. Y is equal to A, which is 0.5, right? Okay. E, right? What's our K again? Our K is ln what's this? 9885 times t, right? A e to the k t. Get it? Okay. Now, let's read this one in here. How to solve the half-life problem, okay? Logan, let's read.
Express given values in the form y equals a times e to the power of k times t.
Thank you, right? So we already got this form, right? A is 0.5, initial value. E is basically your natural number, right? K in there is ln of b, which is 0.9885 t, right? That's time ln, okay? Let's read step number 2, all right? Adam, go ahead.
To solve for half-life rate k, make y be the half value.
Okay, so what we're gonna do in here, let's make this what? Half value of 0.5, right? So what's the half value of 0.5, guys? If it's 0.5 initially, what's half of 0.5? A quarter, or 0.25, right? So with that being said, we can just basically write this one as what? 0.25. Get it? Okay. Is equal to what? 0.5 e to the ln what's this? 9885 t. Good? Okay. Now, let's continue with the solving for what in here? T, right? To solve for t, what do we do first? How do we get rid of 0.5? Very good, right? Divide both sides by 0.5, right? So with that being said, this will cancel out. What is this? 1/2. Good? Is it 1/2, right? Okay. Is equal to what? Well, e to the ln will just be cancelled out, right? You good? Right? So basically this one will just be what? 0.9885 raised to the t power. We good, guys? Right? By inverse rule, e to the ln will just cancel out. That basically is 0.9885 raised to the t power, right? Okay. So with that being said, what do we do then to get this one in here? Convert it into logarithm, right? So how do we convert this one into logarithm, guys? Logarithm, what's the base? 0.9885. Of what? In half. Is equal to what? Right. And from there, you can basically get your half-life time already, right? So what's that half-life time in here? What's that gonna be on your calculator? Logarithm base 0.9885 of 1/2. What is that equal to in terms of our time element, right? It says in here to round it off to what? Nearest day, right? So how long will it take to get its half-life? So let's put it in here. Check it out how we're gonna get it, okay? Let's go here. Let's go to our functions. Let's go to, where is that one? Logarithm, there we go. What's the base again? 0.9885. And then in here, we're gonna put what? 1/2, right? So how long will it take to reduce to its half-life? 60 days, right? So to the nearest days, it will take approximately 60 days for half of that iodine 125 to run out. Are we good, guys? Get it? Okay. Once again, how much? 60 days. Are we cool? Okay, now let's see in here. If I go back in there for step number 3, right? So if I go in there and to solve for t in there for its half-life time, let's see if that's gonna work for that. What's that gonna be in there? Negative ln 2, right? Okay. Divided by, okay. What's our k again a while ago? Our k a while ago is how much? That one, right? That's our k, right? So if I put k in there, that will be what? ln of how much is that? 0.9885, 0.9885. And as you may notice, it basically is the same, right? So as you may notice in here, let's read step number 3, all right? Let's read step number 3 for such. Giselle, go ahead.
Solve for k equals minus in2 over t as exact last.
Thank you, right? So that is the k, or the, what you call this, the constant, right? Or the rate. But in here, since we're solving for the half-life time, if you just flip these two, this t and the k, because in here, based from this problem, you just want the half-life time, right? Flipping these two, that means t, or the half-life time, is basically what? Negative ln2 over k, right? If you use that one, negative ln2 over k, what's your k again? ln of 0.985, you're basically gonna get the same answer, right? So I can put in here, or you can use that same as formula as well. T is equal to what? Negative ln2 over k, right? And what is your k in here? That basically is your k. So if you do that one in here, you're gonna arrive at the same answer anyways, even without doing the conversion from exponential to logarithmic. Just use that formula right away, you're gonna get the answer, right? Either to solve for the half-life time or for the rate itself. Are we good? Right. Let's read step number 4. If it's needed, what do we do then? Lexani, go ahead.
Rewrite this formula with some k values to predict future values.
Right. This is what we call extrapolation, right? If you're predicting future values, then that means you can use that formula, right? AE to the KX power, okay? Let's go back to the last question in here. What did it say in here? Number 32. Anne-Marie, go ahead, please.
Run it, do you want me to read it?
Yeah, please.
Okay. Run an exponential model representing the amount of iodine 125 remaining in the tumor after 2 days. Then use the formula to find the amount of iodine 125 that would remain in the tumor after 60 days, round to the nearest tenth of a gram.
Thank you, all right. And we can verify that one once again. Once again, our formula, y is equal to A. What's your A again? 0.5, right? Initial value. E, right? What's our K once again? It's ln 0.9885, right? So ln 0.9885, that's basically a power, right? Times T. Get it? Now, we're gonna change that T into how much? 60 days, okay? So if I evaluate this function at T equals 60 days, what you're gonna get? 0.5 e to the ln 0.9885 times once again 60. Guys, by the way, guys, in multiplying it by 60, you don't put the 60 multiplied to 0.9885, okay? You multiply 60 outside of that ln itself, right? So again, this 60 should not be multiplied to 0.9885, but instead multiplied to this entire thing. Well, to this ln 0.985, right? Anyways, what you're gonna get in here? Put it on your calculator, guys. What you're gonna get for your y equivalent to? How many grams will be remaining after 60 days? Check it out. Let's put it in here, okay? Once again, y, okay, A, which is what? 0.5, E, right? Shift 6, right? ln, what's that again? 0.9885, and then multiply it by 60. How much was left after 60 days, guys? To the nearest what? Did it say 2 decimal places? Tenth of a gram, right? So in short, 1 decimal place, right? What's that gonna be? Sibilai? Is it 0.2 or 0.3 grams? 0.2, right? Right, because after 2 is 4. But basically, if you want to write it off to 2 decimal places or hundreds, that's 0.25, half of 0.5 grams a while ago, right? Which confirms that our half-life is after 60 days. It's going to reduce to half its size or amount. Are we good, guys? Right? By the way, what is iodine 125, right? Let's see. So as you may notice in there, iodine 125, basically some of the uses for radioactive elements in our like biomedical research is tracer, right? Tracing if or imaging, right? If there are some like cancerous cells, typically they would inject with radioactive isotopes. We good? Definitely, obviously, you don't want radioactive elements on your body. That's why it has to be excreted out of your system, right? Good. But how long will it take? It says in here 60 days, right? So in basically 2 months, right? Even in like cancer therapy, right? The radiation therapy, it takes time, right? To excrete those radioactive elements out of the system because of this half-life scenario. Are we good? Right? Thank you, McKinsey. Any